This is a visual representation of a bipartite graph. Vertex set V is the union of the two disjoint sets L and R. Set L is labeled as L1, 2, 3, 4, 5, 6, 7, and the set R is labeled as R1, 2, 3, 4, 5, 6, 7, 8. So sets L and R represent the two parts of the bipartite graph. L is on the left and R is on the right. The vertices in the set L are only connected to the vertices in the set R and vice versa. The lines connecting the vertices represent edges. They show which vertices in set L are connected to which vertices in set R. A matching in a graph is in the set match M, which is the edges without common vertices. So the matching M here has a cardinality of 4, which means that there are 4 edges in the matching, and the edges that are part of matching M are highlighted, which indicating that the edges are selected to represent the matching. And let's talk about vertex colors. Matched vertex are blue, which indicating they are part of the matching M, and unmatched vertices are orange, which indicating they are not included in particular matching. And the objective of the matching in a bipartite graph often involves to find the maximum matching, which is the matching with the highest number of the edges. In this case, the matching with cardinality 4 is not the maximum possible because there are vertices in set R that are not matched and could potentially increase the size of the matching. A matching M is a set of edges without common vertices. If a vertex is connected to another vertex via an edge in M, it is considered matched, and if not, it is unmatched. A matching is the maximum if you cannot add any more edges to it without violating the matching property, which is no two edges share a vertex. This doesn't mean the matching is largest possible, just that it is local optimal and cannot be improved by simply add another edge. So a matching is maximum if there's no matching that includes more edges, and this is the largest possible matching for this graph. Well, the maximum matching is always the maximum. The reverse is not always true. A maximum matching is not necessarily maximum. A maximum matching is the one where you cannot add any more edges. Well, a maximum matching is the largest overall, and there's no any other matchings with more edges. To form a path from R3 to R8, we must follow the edges that alternate between being in and out of the current matching, starting from an unmatched vertex, and given that R3 and R8 are already in the same set, they cannot be directly connected by a path, right? So the path must go through the vertices in other set L, and R3 is already matched, so we would looking for a path that starts from an unmatched vertex from L set that connects to R set. Then we continue the R through the other vertices in L. If R3 is already matched, it wouldn't be the starting point of the augmenting path, but it would be a vertex along the path. So for clear understanding, we would need to identify an augmenting path. The Hopcroft-Karp algorithm would be used to find such paths to incrementally improve the matching until it becomes the maximum. From this matching, we can tell whether it is maximum or maximum by adding more edges without sharing vertices. If we can add another edge without sharing vertices, then this matching is not a maximum. So the Hopcroft-Karp algorithm would help us in finding the augmenting path more efficiently, potentially leading to a maximum matching. An M-alternating path in a bipartite graph is a path that alternates between edges that are not in matching M and the edges that are already in matching M. We're starting with an unmatched vertex. The path goes through an edge not in M, then go to an edge already in M, and this continue in this pattern. An M-augmenting path is a special type of M-alternating path that starts and ends with the edges not in matching M, which means it starts and ends with unmatched vertices. This is important because it implies that if the edges along the path are flipped, which means the edges not in M are added to the matching and edges in M are removed, then the size of the matching increases by exactly 1. Because it starts and ends with the edges outside the matching, an M-augmenting path must contain an odd number of edges. This is because the path alternates between the edges in M and not in M, and starting and ending outside M forces the path to have one more edge outside M than inside. Using M-augmenting paths, if we want to find a path from R3 to R8, we have to begin the search for an augmenting path from an unmatched vertex in one set, not from a matched vertex such as R3. So R8 is unmatched, so it could be the endpoint of an M-augmenting path. An augmenting path could potentially pass through R3 if R3 is currently matched as part of an edge in M. The path flips the matching along its way, leaving R3 unmatched at the end of the process. The actual path from R3 to R8 could depend on the current state of the graph and the matching M. We will need to find an alternating path that includes R3, leads through other unmatched and matched edges, and concludes at R8. If R3 and R8 are both to be endpoints of an augmenting path, they would not be directly connected, but would be endpoints of different paths or parts of larger alternating cycle. M-augmenting path is a path that alternates between edges that are not in the matching M and the edges that are already in M. So let's start from an unmatched vertex in L set and ends at the unmatched vertex in R set. The existence of the M-augmenting path indicates that the current matching M is not the maximum, as it can be augmented or improved by swapping the edges along the path, which means we just remove the matched ones and including the unmatched ones. The edges highlighted in orange from the M-augmenting path P, they represent a sequence of edges that, if the matching status is swapped from the matched to unmatched or vice versa, will result in a larger matching. This is fundamental in the algorithm like Hungarian method or Ferguson method for finding the maximum matching in the bipartite graphs. The matching highlighted in blue, which represented as matching M, which consists of edges that do not share common vertices. It is a set of pairs such that no two pairs have a vertex in common. The matching M prime, which is the symmetric difference of M and an augmenting path P, which contains one more edges than the original matching M, indicating that we found an augmenting path and we can utilize it to increase the size of the matching. But this new matching M prime is still not the maximum matching. There are still augmenting paths available that can further increase the size of the matching. There exists another combination of the edges that would result in even more edges being matched without any shared vertices. We add vertices L6 and R8 to the matched vertices. This means that in the augmenting path P, these vertices were previously unmatched, but now they are matched, which contributing to increase in the size of the matching M. This lemma demonstrates that just by using M-augmenting paths, we can create a new matching with one more edge than current matching M. An M-augmenting path is a path that begins and ends with the unmatched vertex and alternates between edges that are not in matching M and edges that are in M. And just we use the symmetric difference operation to create a new matching M prime from the current matching M. The M-augmenting path is called the symmetric difference, which is defined as the set of the elements that are in either set of X or set Y, but are not in both. The symmetric difference is commutative, which means X symmetric difference with Y is equal to Y symmetric difference with X, and associative, which means the symmetric difference of x and y symmetric difference with z is equal to x symmetric difference with the symmetric difference of y and z. This means that the order in which you perform the symmetric difference operation doesn't affect the result. For the symmetric difference, the empty set acts as the identity element, meaning that x symmetric difference with empty set is equal to x, and furthermore, each set is its own inverse with respect to the symmetric difference because x symmetric difference with x is equal to empty set. This lemma suggests a way to iteratively improve a matching by finding an M-augmenting path and then using this symmetric difference to toggle the edges along the path to obtain a larger matching. So this process is repeated until no M-augmenting path can be found, at which point this matching is maximum because we can't enlarge by any such path.